Welcome to Day 16 of Daily AI Wizard, my incredible wizards. I'm Anastasia, your thrilled AI guide, and I'm absolutely buzzing with excitement today. Have you ever wondered how AI can learn to see, hear, or even understand language just like a human brain? We're diving into deep learning, a powerful evolution of neural networks, and it's going to be a magical journey. I've brought my best friend Sophia to share the excitement. Over to you, Sophia. Let's compare deep learning and neural networks, and I'm so thrilled. Neural networks typically have a few layers, suited for simpler tasks like basic classification. Deep learning uses many layers, tackling complex tasks with greater depth and accuracy. It's better for things like image recognition or natural language processing, where patterns are intricate, but it requires more data and computation power to train effectively. For example, a deep network can power language translation systems like Google Translate. It's a magical evolution in learning. I'm so excited to explore it. Why use deep learning? Let's find out. I'm so thrilled to share its benefits. It handles complex, non-linear patterns in data, capturing relationships other models can't. It's great for big data and datasets with many features, scaling well for large problems. It automates feature engineering, like extracting edges in images, saving us time. For example, it can detect objects in self-driving cars, ensuring safety on the road. Deep learning often outperforms traditional models in accuracy, making predictions more reliable. It's a magical tool for modern AI. I'm so excited to use it. Let's see how deep learning works, and I'm so excited to break it down. It stacks many hidden layers of neurons, creating a deep architecture for learning. Each layer learns different features, building complexity as data passes through. Lower layers detect basic patterns like edges or shapes in images. Higher layers combine these to recognize objects or concepts, like a car or a face. It's trained using backpropagation and gradient descent to optimize predictions. It's a magical hierarchy of learning. I'm thrilled to understand it. Deep learning has key architectures, and I'm so eager to share them. CNNs, or convolutional neural networks, are perfect for images, capturing spatial patterns like edges. RNNs, or recurrent neural networks, handle sequences like time series or text, remembering past data. Transformers power language tasks, like those in ChatGPT, understanding context in sentences. For example, a CNN can classify images, identifying cats or dogs with accuracy. Each architecture has its own magic, suited for specific tasks. Let's explore their powers. I'm so excited. Training deep neural networks is fascinating, and I'm so excited to share. The forward pass sends data through the layers, making a prediction at the end. We calculate the loss by comparing the prediction to the actual value, measuring error. The backward pass, or back propagation, adjusts weights to reduce this loss across all layers. We optimize using gradient descent with a learning rate to control updates. With more layers, more computation is needed, but the results are powerful. It's a magical training journey. I'm thrilled to learn it. The vanishing gradient problem is a challenge in deep learning, and I'm so determined. In deep networks, gradients can become tiny as they propagate back through layers. This slows or stops learning in early layers, making training ineffective. It's common when using activation functions like sigmoid, which squashes values. We can fix it with real U activation or better weight initialization techniques like Xavier. It's a challenge for deep magic, but we'll overcome it. Let's solve it with AI tricks. I'm so excited. Deep learning requires the right hardware, and I'm so eager to share. It needs lots of computation because of the many layers and parameters involved. CPUs are slow for large deep networks, taking too long to train effectively. GPUs offer faster training with parallel processing, handling many calculations at once. TPUs, designed specifically for AI, are even faster, speeding up training further. For example, training on a GPU can drastically reduce time for deep models. Magic needs the right tools. I'm so excited to explore this. Deep learning has incredible real-world applications, and I'm so inspired. It powers image recognition in self-driving cars and security systems, identifying objects. In natural language processing, it enables chatbots and translation tools like Google Translate. In healthcare, it diagnoses diseases from scans, improving patient outcomes with accuracy. It also drives recommendation systems on platforms like Netflix and Spotify, personalizing content. Deep learning transforms the world with its capabilities. It has a magical impact on society. I'm so thrilled by its reach.